So let's start with our asymptotes. And then we'll go to our derivatives. Vertical asymptote, that happens at a non-permissible value. What can't x be? X can't be -2, so that would mean that we would have an asymptote at x equals -2. Horizontal asymptotes are not going to affect any of our first derivative or second derivative tests, but are going to be important as far as the final graph goes. How do we find horizontal asymptotes? Look at the limit. What happens is x gets really, really big, either positive numbers. What happens is x gets to really, really big negative numbers. Well, as x gets really big numbers, the +1 and the +4 won't matter anymore. And you're really looking at 3x over 2x, which just simplifies to 3 over 2. So we have our asymptotes to start with. Now we can go to our derivative, see if there's any local mins or local maximums. And you can use the quotient rule. Keep the bottom the same. Derivative of the top minus keep the top the same. Derivative of the bottom. Over the bottom squared. Simplifying the top here. Distributing, we're going to get a 6x minus a 6x, and then a 12 minus 2. Will just equal 10 on the top. In order for this fraction to equal 0, the only way a fraction equals 0 is if the numerator equals 0. So I hope you can see that f prime of x never equals 0. So as far as figuring out where things are increasing and decreasing, we still make our number line. We still have to put our non-permissible value on here. There are some questions, I think there was one in your homework, where it never equaled 0. You can still make your number line and find out, is the whole function increasing forever, or is the whole function decreasing forever? But in this case, we're going to put our non-permissible value, because that's where our asymptote is going to be at -2. And if we plug in something less than -2 or greater than -2, it's always going to be positive. I can see that right away by my fraction here, because the bottom is squared, so that's always going to be positive, except when it's equal to 0, which is the non-permissible value. And the top is 10, which is always positive. So this function is going to be increasing in both of those sections. Now for our second derivative, a couple of different ways you can go to the quotient rule again, or if you'd like, you can take the fact that f prime of x is equal to 10 2x minus 4 to the -2, and then you would just have a power rule with a chain rule. That's a good question where the -4 comes from. It never existed. I was just going to write a +4. I was just hesitating for effect and to make it more exciting as we went along. Okay, yeah, it is +4. And then when you take the second derivative of this, and of course it's a chain rule, so we're going to have to multiply this by a 2. So we get f double prime of x. At this point, I'm going to write the -40 on the top. I'm going to move this back down to the bottom of my fraction, and note that it also is never equal to 0. We still, though, could have a change in concavity at -2. So if we plug in a number less than -2, like a -5, the top of our fraction is always negative. A -5 on the bottom of our fraction to the power 3 would be negative, making this section positive, concave up. And after -2, like 0, when negative over a positive would make that section negative. So we do have a change of concavity. However, -2 is not an inflection point because it was a non-permissible value. So now we've got as much as we could for maxes, mins, increasing, decreasing inflection points. We'll have none of those points to actually graph. When we look back at our original equation, I hope you can see that you can find the y-intercept rather easily. If you plug in 0 for x, you will get 1/4 for y. So there's 1 point. X-intercepts, again, the only time that a fraction is equal to 0 is if that numerator of that fraction is 0. So we need 3x plus 1 to equal 0, and that'll happen at -1/3. So now we have our x-intercepts and our y-intercepts as well. We've got our asymptotes. We know where it's increasing, we know where it's concave up and concave down. So we can go to our equation, draw our asymptotes in with a dotted line. I like to use red. Vertical asymptote was at 3/2, is that right? Labeling our 2 points with -1/3, 0. And 0, 1/4. And we know it's increasing in both sections, concave up and concave down. Now that'll tell us that in this part, towards those asymptotes, it'll look like that. And the only way in our domain less than -2 that we can have a function increasing and concave up is if it's in this section. Sometimes I feel like when you're graphing something, if you have something in a section and you don't have a point labeled, it feels a little bit wrong. It's not hard to get a point in there. You just have to go back to the very first way you learned how to graph was just making a table of values and getting a point. If I plug in -3 in for x, I plug that back into my original equation, I'm going to get a value for y. On the top, I'm going to get -8. On the bottom, I'm going to get -2. -8 divided by -2 is 4. -3, 4. Looks like I scaled things perfectly. And there we have our final graph with a point labeled in each section. We've got the concavity showing. We've got it showing that it's increasing over the entire thing.